So this presentation is on the probability distribution of a continuous random variable. And this is in modules 11 and 12 in the OLI textbook. It's topic 2 in the corresponding section of the workbook for the class, the module 11-12 section of the workbook. So that's starting on page 327 in the November 2020 edition of the workbook. And so your three sources of information are going to be the textbook first, but there's also the write-up in the workbook, and then there's this PowerPoint presentation that I'm about to do. And so here it goes. So this PowerPoint presentation is about the probability distribution of a continuous random variable. So I'm using material from the OLI online textbook, module 11. This part is pages 148 through 162. And also from the workbook, which is from module 11, topic 2. So this the definition of continuous random variable is already partly familiar to you, but the definition I'm giving here generalizes what you already know a little bit. Before, we were just talking about random variables in the connection with the populations and samples, where you were looking at a measurable characteristic of an individual in the population. Here we also want to include situations like we were talking about with rolling dice earlier, where there's not really a population, there's an experiment that you could do infinitely many times. It's not a huge difference, but a random variable for a repeatable experiment is a function whose domain, the set of inputs to this function, is the sample space of the experiment. Consider all the things that might happen when you do the experiment, and those are the inputs to the function. And then the range of the function, the outputs, what it gives you, is the variable that you're measuring. So for example, the repeatable experiment could be to bake a cake using a particular recipe, and then you measure its weight in ounces, and the weight is a continuous variable because fractions are possible. This is hardly different at all from selecting a random person and measuring their weight. In the latter case, you have a finite population of people to choose from, but with baking the cake, you're just thinking about all the infinitely many times you could bake the cake in the future. But either way, once you have an outcome or a selected individual, you just measure something. And if that result could be any real number in some interval, including all the little fractions in between, that's a continuous variable. Now, the probability distribution of a continuous random variable, it's a continuous non-negative function intended to represent what the percent frequency density histogram would become if we could collect an infinite amount of data. I'm going to show you what I mean by that in pictures in the next few slides. So, how does a histogram change as you collect more data? Here I have two histograms that I imagine are for different samples, both samples taken from the same population. On the left, the histogram was made with a smaller sample, fewer individuals. And on the right, it was made with a bigger sample, with more individuals. If you remember, we're using Sturgis's rule to decide how many bars to put in the histogram based on the sample size. So the more individuals in your sample, the more bars you have. The area of each bar is the percent of the individuals who fall in your sample, or the percent of the repetitions of your experiment. So each bar is a percentage, and all the areas of the bars add up to 100%. It's the areas that add up. The area of a bar is the width times the height of the bar. You multiply to get the area of each bar, add those up, and that's what comes out to be 100%. Now, if you imagine collecting data forever, you'd get more and more little bars. The total area stays the same, 100%, but with hundreds of little bars, the envelope on top of the bars becomes smoother and smoother, and you can imagine what it might come to if you could just keep going forever. So that curve that you think it might be approaching, that's the probability distribution. Now, it's only theoretical. You're just using your imagination to fill in between the stair steps. So we don't know if it's actually right. It's just a theory or a hypothesis. And the business of statistics is to test hypotheses. Now, once you've got a continuous probability distribution, so you've made a curve, perhaps you've even made a formula for that curve, how do you use it? It's for finding probabilities. The probability that your variable, your x, will be between 2 points A and B. You find that by finding the area under the curve between A and B. So now you see why these curves, they have to be positive. You can't have like a negative probability. So it all stays above the x-axis. And it needs to be a nice, smooth, continuous curve so we have some way to find areas. And that's it. The challenge is just to find the areas once you have the curve. Now, this kind of curve that we're talking about here, these probability distributions, they're sometimes referred to as probability models. What's going on with this word model? Well, you're using the density function to make a prediction. If you repeat the experiment many times in the future, you're trying to predict what percent of the time will X be found to be between A and B. But you're trying to make a prediction for what would happen if you just repeated the experiment over and over again forever, and you can't do that. Okay. So And your model, whatever it's based on limited information. And so it's a model in the sense that, like, a toy car is a little bit like the real car, but it's not necessarily completely correct. Now, where do these probability models come from? Okay, it could be from your imagination, just filling in between the stair steps of the histogram, or your curve-fitting methods in math to make a polynomial or another function to kind of fit the histogram. Either way, you're looking there at data that you've collected in the past and filling in what you think will happen in the future. So imagination would be one place that the models could come from. Another would be scientific theories. They're parts of physics, statistical and thermal physics, or quantum mechanics, where they have some basic principles that seem to be true about nature in general, and then they can use those principles to figure out what some distributions should be. And in physics, at least, those turn out to be very reliable. And the third source of these models is simulations, where you throw in a whole lot of assumptions and use computers to just try out and simulate the experiment many times and see what the percentages come out to be. So can you ever find out for sure if a probability model is really correct? No, not really, because you can't repeat the experiment infinitely many times. But you can compare the model against data and try to decide if the difference between them is or is not significant. If your future observations begin to differ significantly from the model, then you begin to doubt the model. Or if they continue to match pretty well, you might continue to use the model for decisions, personal or business or policy decisions. It might be based on the model if, so far, it's doing pretty well. So, working with these continuous probability density functions is going to require us to find areas underneath them. And so you must be worried, well, how can I find the area underneath an arbitrary curve? The general method for this is called the integral calculus, invented by Newton, but that's not a prerequisite for this course, so we can't use that. So we're going to limit ourselves to areas of simple shapes like rectangles and triangles, or curves where we have functions available in Excel or on calculators to find the areas for us. So here are some examples of continuous probability density functions. Here's the uniform distribution, where all the different x values between A and B, they all have equal probability, so the curve is equally tall all the way across. And you can find an area underneath this real easy because you can find the area for a rectangle using the base times the height. And here's a triangular distribution with a vertex here at HK. K is the height. Area of the whole triangle is half the base times the height. Of course, for both of these pictures, the total area underneath each one of these is 100%. But a lot of times you're trying to find the probability is just the area in some little wedge, some little piece underneath the curve. But you can still cut those up into rectangles and triangles and then use these formulas to find the areas. So here are two more examples of continuous probability density functions. The normal distribution, this kind of bell-shaped curve that we've already talked about a little bit. We talked about roughly normal distributions before that were symmetrical, unimodal, and without modes. This thing that I've drawn here is not just roughly normal, it's really normal in the sense there's a very specific formula for this curve. And we can use Excel to get areas underneath it. There's a function called norm dist, and I'll demonstrate that more with Excel. So we'll leave that out of the PowerPoint for now. Right now I'm just trying to show you, here's a couple more of these distributions. Normal distribution, the chi-squared distribution. Which again, it's like every time you see a distribution that's skewed to the right, don't think it's necessarily chi-squared. It's chi-squared has one very specific formula for it, and others may look a little bit the same without having exactly that same formula. Okay, so that's it for the presentation. Do go and take a look in the workbook and read the chapter in the Module 11 in the OLI textbook before you get started on the homework, but then it should go pretty easily. And as always, send email, let me know if you're having trouble. And that's all for this. See you next time.